Hello YouTube viewers, welcome to my channel Science to Technology. In today's show, Rocket Monday, we're gonna talk about Radioisotopic Thermoelectric Generator RTG in depth. So let's dive deep into it. So what exactly is the need for this RTG technology? Well, problem is that space is weird. What does that mean? That simply means it has brutal temperature swings, as in a spacecraft that is exposed to the sun, the surface on basically Earth's area, basically one astronomical unit, that puppy can easily touch 120 degrees Celsius. That's hot. Now, again, that in itself is not that bad, given the fact that shadow can easily go as low. If you stay in the shadow, you will go as low as minus 270 degrees Celsius. That's 3 Kelvin. Like, almost everything becomes liquid at that point in time. And most things become solid because that's 3 Kelvin, very close to absolute zero. So that will cool you a lot. So you will go through the sun side, you're like, heat it up. You go into the shadow, freeze it up. That's brutal. And inverse square law, that's a law of physics, law of universe. That simply means sun's power falls off surprisingly dramatically. For example, if you deal with solar panels, they generally will say they are rated at 1 kilowatt per square meter, bit more plus and minus. But generally, if you go outside of the Earth's atmosphere, you are looking at 1360 watt per meter square. Now, wait a minute, what the hell happened to that 300 watt? Your atmosphere ate it. So that's the total oomph that is available in one astronomical unit. Basically, if you go to moon, more or less the same. However, if you go to Mars is a bit far away. That's 600 watt. You started with more than 1300, you drop to 600. Now you're still in self regions also. Now you're going to gas giant, like let's say Jupiter. Yeah, that puppy has dropped to 50 watt per meter square. That's magnificent drop. That's like, damn. You go to Pluto, that's 1 watt per meter square. That is so low. And again, some people say that mathematically, because of the angular size of sun, if you are on Pluto's surface, like let's just say you are actually standing, it will be hard to find where the sun is. Like, it would be difficult because again, sun is not that bright. 1 watt per meter square is not that much. And because there is no atmosphere, all other stars will be much brighter. So yeah, you will have a hard time finding where the heck is sun. Oh no, you sure that is sun? Because again, you will see other things that are behind sun also. So it will be very confusing. And again, that's just like, okay, 1 watt per meter square, not that end of the day. Problem is thermal radiation capability. Like, for example, let's just assume this is as a black body, how much oomph it can dissipate. Yeah, you are looking at 418 watt per meter square. If it's not insulated properly, this puppy will freeze. So that's the issue. That's why if you are sending something into deep space, even as far as Mars, you have to compensate for how the heck it's not going to freeze over. I'm not joking. There are literally heater elements which are just plutonium encased in a basically epoxy graphite and all that, just so it acts like a 1 watt heating element. Nothing else. It's just a heater, just so the spacecraft does not freeze. Because whenever you are talking about that much loss of power, of course, we work our ass off to insulate the hell out of it. But again, no insulation is perfect. It just delays everything. So we still need some heat source. And this is the primary reason why when you are talking about moon missions, Mars mission, you not only need power, you also need heat. And again, God help you if you are even thinking about deep space mission. Like, pushing things to Jupiter is hard. Like Saturn, Venus, Earth, Mars, Jupiter and Saturn is like upper limit of what solar can do. Go further than that, like Neptune, nothing. Pluto, don't even think about it. Again, you will literally freeze up even if you have a ginormous solar collector, because your radiative heat loss would be so high. So we do need something that is nuclear. So nuclear does not mean just use any Tom, Dick and Harry nuclear thing, simply because there is a very strict checklist of all the materials that have a decay. So first thing is high specific power, meaning this puppy has to be hot. Without active fusion or fission, it should be hot. Now, many things have that. So thankfully this. How do you know it's hot enough? Well, it's supposed to be glowing red hot. That red is actually a black body temperature radiation. It's like, if you can see it, if your eyes can see it, and it looks flat out red or glowing red like a low power red LED, yeah, it's hot enough. This generally means it's above 400 degrees Celsius. Heat metal up to most metal will start to glow. So red hot is the temperature, quote unquote, and it should have ideally a very long half-life, as in 50 to 100 years, especially if you want to do deep space mission. Because you might be like, okay, half-life, okay, what if it only loses 25% power? It's just that your loss because of temperature drop would be dramatically more. You want something that almost changes nothing, then with the loss and the degradation of electronics and all that jazz, then you will have some decent power. So 50 is bare minimum. Like generally you will like, oh, what if the mission is only 10 years? Like again, sending things to Pluto, 10 years is enough. It's just that if your half-life is, let's say, only 20 years, the degradation would be so fast that by the time you reach Pluto, you would have lost too much of power, too much. So of course you can compensate by having bigger and bigger, but at that point your rocket will not be able to take off from Earth. So generally find as long life as possible, like 80 years, 70 years, 100 years, those are the sweet spot for deep space. And ideally alpha emitter, meaning this puppy, you know all 4 types of radiation. You have alpha, beta, gamma, neutron. So, and be mindful whenever you're talking about radioactivity, there are spontaneous events, which meaning nothing happens, nothing, and boing, neutron came out. It's like, what the hell? Yes, it does happen. So ideally you want 99.999% output to be alpha. Why? It's the easiest to block, meaning with few aluminum foil you can blockade it, like nothing else. Your electronics or your sensor will be overwhelmed by alpha noise. So that's a very desirable factor. Now that does not mean plutonium only has alpha. Like of course if you have sensitive enough detector, it will detect other things, but it's just like, you know, for every 1 gamma photon, like, you know, that's a 1 in a million event, or neutron 1 in a billion event, that sort of thing. And stable ceramic compound has to be there, so it can be boom proof. What does that mean? That simply means these things are naughty puppy. So generally you want to contain in such a way that you put in a rocket goes kaboom, you are like, I'm fine. This thing ideally should be in one physical intact, and even if they crack, it should be chunks. It should never become powder. That's the first requirement. It should not become powderized, or hell no if it can melt. Like if it's meltable at rocket boom temperature, they'll be like, yeah, we are not using it. So ideal aim is that even if rocket goes kaboom, it should fall off as a full chunk. And even if, let's say, during ascent or something like that bad happens, it still should be chunks. It should not turn to dust, nor it should melt. So that's why ceramic compound structure, basically oxides, have to be there, and they have to be stable oxide, thermally, physically, temperature wise, all of those things. So production should be available. Of course, there is no point of having a magical material if you can't buy it. For example, magical material number 1, plutonium-238. Yeah, it's magical material category simply because it's no longer available. We did amazing thing with that. That's Voyager's record. This is Apollo era. We did amazing thing with that. It's just that after Cold War, the weapons nuclear reactors have been shut down, basically reactors that were breeding things. So yeah, the supply of plutonium-238 is done. Like NASA has fixed amount, and they are fighting vigorously to figure out how to utilize it properly. That's why some missions literally has been scrapped. It's like, we had to plan for this, we don't have enough plutonium. They're trying to find alternative, but yeah, supply chain of plutonium-238 is gone. The Russia was like, you know, selling some amount, but recent Russia boom boom event with Ukraine, I'm pretty sure you can't buy anymore. So there is a push. And again, European Union is also wants to get into the game, so they are also pushing for it. Americium-241. Now this puppy is the new darling right now of European Union and NASA. It does have some penalty. First, it's colder. It's not as hot as like red hot, so it's colder, and it does have naughty radiation, as in like alpha, beta, gamma, those sort of things. But again, not too much, not too much. It can be managed, and again, your household might already have it. Smoke detectors have that, Americium-241. So it's available because it's output of civilian nuclear reactor. It's like, shut up, take money, that kind of thing. It's like, how many tons you need? But again, best case scenario, you're still gonna build something that will be less powerful than plutonium system, but it will be so cheap that you can actually afford it. So that's the nuclear fuel aspect of it. So how the heck we take the heat and make it into electricity? That's where Seebeck effect comes in. Now Seebeck effect is basically the magical trick of converting thermal delta, T delta, into useful electrical work. As in, hot should be very hot, cold should be very cold. Tada, is the delta between temperature. It's not like cold has to be 0 Kelvin or let's say 0 degrees Celsius. No, hot can be basically the cold side could be 100 degrees Celsius, the hot side would be 500 degrees Celsius. It will work. So basically the delta between those 2 points define how effective it would be, and it directly converts into electricity. And the biggest part is there is no moving component, nothing. There is nothing that physically moves. And how do you achieve it? Surprisingly easy. All you need is two different conductors that are exposed. Basically, you have two conductors creating a loop. One side is hot, one side is cold, and voila, you generate some electricity. And if you're like, okay, I want more power, increase the delta. Higher the delta equals more power output. Now, that is super easy, and you most likely you have a thermocouple in your home. That's easy. Shut up, take money. That's not any issue. Problem is, if you really want to generate power on it, not just as a temperature thermometer, you want to generate power from it, yeah, you need something that is unique, as in conductor of electrons but not of heat. As in, it should be almost like how we figure out for insulator, like, you know, insulator that does not allow electricity to pass through. You need that property but inverted, as in thermal energy should not pass through but electrons should pass through. Technical term, phonon glass electron crystal, as in it should block heat like glass blocks heat transfer. And as in, like, what does heat transfer here means? It simply means vibrations and phonon energy. And crystal should be so crystalline that electrons can just flow. So electrons can go YOLO, phonons cannot. So you can maintain that T delta. This is the critical part, because if you just use, let's say, can't I use like a copper or aluminum? Of course you can do that. It does work. It's not great, but it does work. But problem is, if you try to generate power from it, not just detect temperature, if you do that, the metal conductivity, thermal conductivity of those puppies will equalize the temperature. You will not have T delta anymore. So we need something that is like, you know, phonon glass electron crystal. That puppy we need. Now, thankfully, development of semiconductor make this a minor thing. So we have P-type and N-type junction pairing for the strategy, and we generally pair these puppies so you can have enough volt. If you ever look into a Peltier module, it is lots of them. The reason, it's almost like a solar panel. How your solar cell could be very low voltage. It could be like 1 volt or 0.7 volt or like 3 volts. It's not that much more than that. And your plate could be like 40 volt. That's the whole point. We have to pile up those cells in series in order to get the useful voltage. And semiconductor, generally we do not use silicon semiconductor. We use lead telluride. PBTE is utilized in that, and we generally dope them properly in such a way that one side becomes P, another side becomes N. And here's the problematic part. If you can just, like, you know, have heat and convert it into electricity, why don't we use that? Like, why have solar panel? Just have this. Yeah, the problem is this conversion efficiency is poo-poo, like 6 to 7%. And it needs bonkers of T delta, like hundreds of degrees Celsius of delta has to be there. Like one side has to be like 300, 400, other side has to be room temperature, then you might work in those sort of probe system. Like, for example, Martian rover scenarios, hot is actually almost like 400 to 500 degrees Celsius, and the negative is almost 0 degrees Celsius. A Martian atmosphere is some amount of temperature is there, so 0 Kelvin. 0 degrees Celsius. That much delta, then it creates power. So fundamentally is there. And on top of that, efficiency is poor. It does degrade a lot, meaning you are looking at, if you launch a probe, and again, let's say it's a far out probe, like it will take 10 years, you have to calculate 4 to 7% energy loss per year, meaning if you want to be damn sure that it works, you have to plan for like almost 10% power loss per year for a 10-year mission. Only then you're like, okay, how much I need at that loss, then you calculate your starting energy. It does lose power a lot, and that's why we do need something that has a much more flatter half-life. Hundreds of years of flatter half-life, then you'll have like decades should not be an issue. And again, it does self-degrade. That's the issue. Like a Voyager and other things, they have a radioactivity. It's hot enough. It should work. And be mindful, they are so far away, sun's radiation is not heating them up. So cold side is a bit colder. Maybe even from 3 Kelvin, it might have dropped to, you know, maybe 2 Kelvin, maybe 2.1 Kelvin. So why the heck is the power loss is so much? Well, it gets damage from the heat source itself because you have sublimation, meaning literally atoms jump from it. It's just like, doop. It's almost like how you have, let's say, water, and you are not boiling it in, like, let's say water is there. Electron, basically the whole atom can jump, whole molecule can jump out of it, go into phase change, same thing happens, sublimation. Now, because you are heating one side constantly 24/7 into 365, that's very significant. Like you will observe like it's disappearing. It's almost like a filament. Bulb filament actually boils electrons away, something is similar. So sublimation is physically boiling away. Another is atomic diffusion. Because you have such a high heat scenario, and basically, how do we build things? High heat scenario. You have constant high heat scenario. Eventually, those mixture that we have, proper mixture, proper doping, they start to deform, as in like they start to mix, wiggle. So the efficiency goes down. And then you have the old school of thermal stress. So yeah, it's not a long-lasting system. Like you would think, okay, this should work 80, 90 years. It's like, nah, the generator will self-destruct. However, there has been some improvement. There has been some rumors that the scaluride-based generator is under construction. NASA is working on that, and that puppy can push that 6 to 7% efficiency to 8 to 10%. That would be significant. And the biggest thing is this should not have the degradation. Of course, it will also still degrade. It's just that instead of degrading, let's say 4 to 7% per year, degradation could be less than 1% per year. At that point, it's sure to take money. That's huge. But again, very early stage, I can easily expect 20 more years from now to see this actually deployed. So this is Seebeck effect. That's how it actually works. Now we come to advancement, because there is an efficiency ceiling. For example, if you want a solar panel to go above basically, let's say 35% efficiency, you just cannot. Silicon will not let you. So how the heck we reach a solar panel that is 51% efficient? Multi-junction. Silicon is not the only thing. You have basically other things like gallium and basically lead. Other things. Basically, 3 cells are created in tandem. Then you get the full power. So again, silicon will not do. We know the physical limit. It's like it cannot be pushed through. Same thing happens here. Like no matter what we do, if this sort of solid state conversion has some laws that are like thou shall not cross 10%. So question becomes, what can we do? Well, we have to design with plutonium with americium, unless you want to start another nuclear arms race. So americium is so weak in terms of heat output. If you try with RTGs, the current RTG, it will barely produce power. Like it will flat out might not even start. It's like, bro, hot is not hot enough. So yeah, that's the issue. So fundamentally, people are switching to Stirling generator. Be mindful, America has been NASA has been working on it. ESA has been working on it. ESA has been like bankrolling it. It's like, we are serious about this. ESA is like, let's spend some money in it. So Stirling will make americium viable. RTG, normal old school RTG, barely works with americium, and Stirling, if you can swap basically inefficient, like 7 to 8% of RTG with 20 to 30% of these things, then it becomes useful. So you will still have the size penalty because americium is so weak, but you will gain one thing that is very desirable: flat power for years, as in how much oomph you lose per year. So if you started with 100, by the time you are 20 years, you have already lost more than, let's say, 93% of oomph in a plutonium scenario, and then it falls. Like that's why like Voyager is very low. Very low. In 40 years, it has already lost below 80%, and not to mention degradation of per year. Yeah, that's why it's so weak now. But if you had americium, barely any loss after 40 years, barely. Meaning if it was made out of americium in Voyager, it will like, bro, we good. Assuming you could find a way to not have degrading RTG. But essence with this is, this will be used in Moon, and the idea is they know that moving part will not last very long. Like they know, like this is a consumable item, they have wisdom to understand that it will not last very long. So essence is, they're gonna design it in a swappable core design, as in have this puppy, have the americium inside, and if the Stirling breaks, either replace the Stirling, and if too many Stirling breaks, swap out the core. Basically throw away the Stirling, keep the core. Core is the radioactive part. So might as well use it, and it should be very viable in even 100 years. That's the whole essence. So you can have a scenario where it's like, hey, we have this RTG that's not working. No problem. Throw away the non-working part, recycle the metal, and take out the core, put it in a new form holder, so to say. It's almost invert of like, battery swap. It's like you're keeping the battery, you're throwing away the device. Oh, device broke, throw away I'm still using the same battery. So, and it has to be solved. Let that be very clear. We have to figure out how to have RTG. Even if let's just say, assume we figured out how to use remake plutonium, having this will turbocharge it. It's like, bam. And in principle, this should not have that sort of degradation. Assuming it can handle the basically mechanical wear and tear, it should last forever. And yes, there are certain designs that does not have any touching part. They have moving parts, but no touchy. So it could oscillate forever practically. But if we do that, like 10, 20 years, you're gonna have massive like, massive scope creep, so to say. Like, oh, we can do these things. Oh, we have energy for transmitting megabytes of data rather than like, few bits of data. If you ever wonder why don't we have 4K video of, Jupiter and Saturn, it's like, yeah, bits per second. That's the transmission rate. You don't have more energy than that. And not to mention, we are still using the old technology of radio. We have to switch to lasers and then high power. Then you can have like 4K, 8K video coming from there. NASA director has made sure Artemis will have 8K. They made sure like this time we're gonna capture everything and it will be goddamn 8K. So you can be damn sure we actually went to the moon. They're very sure about that. So what can we expect in the future? Well, here's the deal. If we truly want to conquer the moon, like flat out, it's like moon done sorted. And again, unless you have that moon done sorted, Mars is not happening. So we do need a good supply of RTG. Like it has to be a thing that, like right now, we do not worry about where the heck solar panel is going to come from. Again, have you ever paid attention that there was no solar panel in Apollo? Nothing. Supply was not there. So fundamentally, we do need a good supply of this. And heat is useful, even on Mars also. Even though it has like sunlight, it is still desirable to have heat source. And base load power nature of this is great. Now, why not go to nuclear? People are working on it. It's just that it is neutron emitter. All fission reactors are neutron emitters. It's exponentially more difficult. Like you take the worst basically material that is emitting neutron versus fission reactor will be like, brah, bitch, please. No. So fundamentally, there is a wisdom in not forcing it. Like, for example, if you have a rover, I don't want rover moving around with actual full-fledged neutron source. I'm cool if it is like, alpha, beta, gamma emitter is like, that's fine. So fundamentally, and again, it will be like using a flamethrower to light a cigarette. It's unwise. Most of the things, RTG is sweet enough, perfect enough that it works. You have the waste heat that will keep your system warm enough, and you have enough baseload electricity. Like for example, how the heck rover works. Rover charges the lithium batteries. Lithium battery drives the puppy. Once the battery is drained, the rover stops, but again, it does not freeze. The RTG slowly charges it back up, and then it keeps doing. So we do need this sort of thing. And a better technology for conversion, either by switching to better Seebeck generators or Stirling generator. That's a desirable thing. Again, that will help us to industrialize moon a lot. Like we can do things on moon, and deep space mission will become easy. Like this thing, we sent it and then we just like throw it in mission. Like we can't, why didn't we get like, full GG data stream? It's like, yeah, we don't have that much power. Even though at launch, it was a lot of power, but again, divide the power loss year over and 10 years, it's like, yeah. So more power equals more payload, more data. So it's fundamentally desired. And again, private companies are working on it now, that we do need this on moon. Like you cannot do too much on the moon unless you have like RTG is sorted. It's like, bro, hello NASA, 1 RTG please, done. Amazon 24-hour delivery, Blue Origin. So that's necessary. We have to sort this out. Again, nuclear, cool and all, but again, neutron emitters are something to be avoided unless absolutely necessary. So this was my presentation on basically RTG in detail. Hopefully you have liked it, learned from it. In that case, please click the like button, share it amongst your friends. That will help me a lot. If you didn't like it, didn't enjoy it, I urge you to press dislike, press it twice to show me extra disappointment. Please leave a comment because I do try to reply to all of them. Subscribe, press the bell icon if you're free, and as always, thanks for watching.